You know, we usually think of math as this super precise thing, right? All about exact answers, everything being perfectly equal. But what if I told you there's this whole other side to it, a kind of secret language, and it's not for equality at all? Nope. It's all about limits, ranges, and comparisons. Today, we're going to unlock the power of inequalities.
I mean, think about it. The world around us, it's almost never about exact values. It's full of boundaries, conditions, all that stuff. Like, your budget has a max, right? A passing grade has a minimum. And a speed limit, well, that defines an upper boundary. So unlike an equation that just says this equals that, inequalities give us a way to talk about all the possibilities within those limits.
So how does math actually handle this stuff? When you see a sign that says speed limit 55, it's not saying you have to drive exactly 55. Come on, that'd be impossible. It means your speed has to be less than or equal to that number. Or, when you need a 75 to pass a class, that's not the only score that works. It's just the starting point, the minimum. Any score from 75 all the way up to 100 is totally fine.
And to capture all these ideas, math has to go beyond the simple equals sign. It introduces this whole new set of symbols to express relationships like greater than, less than, or at most. This right here is the fundamental language of inequalities.
All right, so to really get a handle on this new language, let's put it side by side with something we all know super well, the simple equation. The difference seems small, but trust me, it completely changes the kind of answer we're even looking for.
Okay, just look at this. On the left, you've got your standard equation, 2x plus 3 equals 11. There is only one answer, 1. X has to be exactly 3. End of story. But now look at the inequality on the right, 2x plus 3 greater than 11. Suddenly, this opens up a whole universe of answers. X could be 4, it could be 5, it could be 100, a million. Literally any number bigger than 3 is a correct answer. See the difference? One gives you a single point on a map, the other gives you an entire territory.
And this right here, this is the vocabulary that makes it all happen. You've got your less than and greater than symbols. These are what we call strict. They don't include the number itself. But what if you want to include it? Well, that's where that little line underneath comes in. It's like an anchor. It gives us less than or equal to and greater than or equal to. Simple, right?
Okay, so we can read them, but how do we solve them? Well, here's the good news. For the most part, solving an inequality feels almost exactly like solving a regular equation. You can add, subtract, multiply, and divide to get that variable all by itself. But, and this is a big but, there is one crucial, absolutely non-negotiable rule you have to know.
So let's start with something that feels familiar. If you have x plus 5 is less than or equal to 12, what do? You just subtract 5 from both sides exactly like you would with an equation. And boom, you get your answer. X is less than or equal to 7. Easy peasy. When it comes to adding and subtracting, the rules are identical.
But here comes the twist. Everything changes, and I mean everything, when negative numbers get involved with multiplication or division. This is the one place where inequalities just totally break from the rules of equations. And honestly, it's the most common place where people make mistakes.
And here it is, the golden rule of inequalities. Listen up. Anytime you multiply or divide both sides of an inequality by a negative number, you must flip the sign. You have to reverse the direction. A greater than becomes a less than becomes a greater than. Now, you might be asking, why? Well, think about it. Multiplying by a negative number basically flips the entire number line on its head. What was a big positive number is now a big negative number, completely reversing the order of everything. Let's see this rule in action, because it makes it so much clearer. We start with negative 3x is greater than 9, okay? To get x by itself, we have to divide both sides by negative 3. The second we do that, the absolute moment we divide by that negative, we have to flip the sign. The greater than immediately becomes a less than, and that gives us the correct solution. X is less than negative 3.
All right, now just like equations come in different flavors, this language of limits has its own little family of types. Each one is designed for a slightly different kind of situation. Let's do a quick tour.
First up, you've got the most common one you'll ever see, the linear inequality. The key here is that the variable, the x, doesn't have any exponents. It's just plain old x. These are basically the workhorses you're going to use to solve most everyday problems with boundaries. Next, we have these cool things called compound inequalities. These are perfect when you wanted to find a range that's stuck between two different values. So a statement like 2 is less than x is less than 7 is just a super compact way of saying two things at once. X has to be bigger than 2,
And it has to be smaller than 7. And then you get into some of the more advanced types, like absolute value inequalities. Now, these are all about distance from 0 on a number line. So this statement right here, x minus 1 is less than or equal to 3. It's really asking a question. It's asking, what numbers are 3 units or less away from the number 1? It's a really great example of how this language can handle some pretty complex ideas.
So, now that we have the vocabulary and the basic grammar down, let's bring it all back to where we started. Because once you learn to see them, I promise you'll realize that inequalities are like this invisible code that's running in the background of our daily lives.
So why does any of this actually matter? Well, because you use this logic all the time, probably without even realizing it. Your weekly budget, that's the at most you can spend. The voting age, that's an at least you have to meet. An elevator's capacity, that's a no more than limit that you really don't want to exceed. This is the math of real-world rules and constraints.
And that really just brings it all together, doesn't it? Inequalities aren't some abstract topic you just learn in algebra class and then forget. They are absolutely essential tools for how we reason about comparisons, about restrictions, and about all the possibilities out there. They help us to find the boundaries that literally shape our decisions every single day.
So, next time you check your bank account, or you step on an elevator, or you even think about the passing grade on a test, just remember that hidden language that's at play. Now that you know the symbols and the rules, what other unspoken limits, all governed by the logic of inequalities, can you start to spot in the world around you?